Okay, hello. I'm very excited to be here to present you what we have been working in order to determine whether we could find model-based computations in dopamine signaling. So let's imagine we moved to a new town and we found our way to a new bakery. However, the world can change, like a road closure. So a model-free reinforcement learning agent would, through trial and error, find their way through experience back to the bakery. However, we know that humans and animals can store internal models of the world, would lead them to quickly infer the optimal path to the bakery. And this would be what model-based reinforcement learning agent would do. So classical electrophysiological studies in monkeys have shown that dopamine neurons behave like a model-free reward prediction error. However, studies in humans have shown that striatal activation with its dopamine-rich region reflect both model-free and model-based prediction weighted by humans' choice behavior. Just in a few moments, I will go through the two-step task that is the task performed by Nathaniel Doe and colleagues in this study, which allowed them to dissociate model-free from model-based behavior. However, it's not possible to directly relate both activity to dopamine activation, so that's why here we wanted to test to what extent is dopamine activity influenced by model-based computations. So let's go first through the two-step task. The two-step task is a multi-step decision-making task which different states are reached probabilistically through taking different actions. So there's an initial choice state where two actions can be taken, action A and action B. Action A with high probability leads to a second step state A, and with low probability to a second step state B, and the opposite for action B. And both states A and B are probabilistically rewarded. So this task allows to dissociate model-free from model-based behavior. So a model-free agent would reinforce actions just based on the outcome, whether it was rewarded or not. However, a model-based agent would take into account both the outcome, if it was rewarded or not, and also the transition probabilities, whether it was like a common transition or a rare transition. So a model-based agent, let's say it takes action A, it got a rare transition and reached state B and got reward on state B. Our next action, we would expect that now it will take action B because with higher probability will return them to state B, where it got reward. So we perform an adapted version of this two-step task on mice. So mice initiated a trial by poking on a center port. This led to a choice state where the mouse could choose between the left and the right port. And each left and right port with different probability lead them to a second state port, up or down, and with low probability to the other one. An auditory cue signaled them which second step port will be illuminated. And poking the second step port will deliver reward in probabilities that change in block. And also before the outcome is delivered, an auditory cue will already signal them whether they are going to get rewarded or not. So let's see here how a mouse does the task. So at this particular point in the task, the highly rewarded second step port is the up one in here, and the optimal choice is to go to the right port. So let's see how the mouse does. So it initiates, it chose left, it got a rare transition but got reward. So the optimal choice would be now to change to the right port. It tries to initiate, goes to the right, now get a common transition, it got rewards, so we would expect to stay with that choice. So it repeats, now got a red transition and got not rewarded, so it's like kind of annoyed. But so here we can see the choice moving average of one session from one mouse. And in green, the horizontal line show would be the optimal choice to take. And as you can see from this plot, mice track which is the best option across many reversals in a single session. And then we look at their choice behavior, and we're very happy to see that actually mice base their choice behavior not only on the outcome, if it was rewarded or not, but also on the transition probabilities, whether they got a common or a rare transition in the previous trial. So this shows us that mice were performing something more interesting than a simple model-free behavior strategy, and actually this choice behavior is consistent with a model-based reinforcement learning strategy. So now that we have some behavior, we wanted to see whether this model-based strategy was reflected somehow in the dopamine system. So to do that, we performed Fibre Photometry. So Fibre Photometry allowed us, we've performed Fibre Photometry on genetically defined midbrain dopamine neurons. So this allowed us to record bulk activity from midbrain neurons in freely moving animals while they were doing the two-step task. So we record from VTA, from ventral tegmental area, midbrain. However, there's evidence that cell firing in midbrain and firing in the projection areas may differ. So we also record from two areas where midbrain projects, nucleus accumbens in the ventral striatum and dorsomedial striatum. So first, we did the most basic analysis, and is just looking at how dopamine activity looks like on rewarded and in non-rewarded trials. So in here, it will appear the Z-score average activity in blue for rewarded trials and in orange for non-rewarded trials. So first, in vertical lines, it will show when the animal actually poke on the different ports. So there's an initiation, then the animal make a choice. We see that there's an increase of dopamine activity. Then there's an auditory cue that is signal them which second step is going to be illuminated. And at this time, even if there's no reward information, we already see that in these two trial types, the dopamine activity already differs. Then the animal poke on the second step port, an auditory cue signal them whether they are going to be rewarded or not, and at this time in the task, we already see that the two signals already differ, and at the outcome time, the reward is delivered for the blue trace, and there the second increase of activity, it reflects reward consumption. So as you may see here, dopamine activity was not just modulated by reward, but we saw a rich pattern of modulation across different stages in the task. So in order to disentangle what behavioral variables drive dopamine activity during the task, we use a linear regression analysis to predict trial by trial dopamine fluctuations and to see how is the impact of different behavioral variables across the task. And then look at the weight of each predictor to see its implications on dopamine fluctuations. So for example, in here, we can see the reward predictor weight, and consistent with the average traces, when the reward information appears, it positively modulates dopamine. However, it does not explain the activity that precedes reward, and this is because in our linear model, we include many other behavioral variables that could explain this modulation. So our main question was if we could see these model-based predictions in dopamine signal. So for that, we constructed predictors that look at what happened on the previous trial and see how it affects on the current trial. So in this case, we constructed a model-free and a model-based predictors, which coded the direction in which a model-free and a model-based action value update on the previous trial would have an effect on the choice made on the current trial. So a model-free agent, if it got a reward on the previous trial, we would expect to increase the value of that choice. But if it didn't got reward, we expect to decrease the value of that choice. However, a model-free agent would not infer what happened on the different port not chosen. Then, on the other side, a model-based agent, we would expect that would update the values not just on the outcome, but also on the transition probabilities. So in this case, for example, if it got rewarded on the down port, we would expect to increase the value of the choice that commonly leads to that same second step port, and to decrease the value of the other port that rarely transitioned to that same port. And if it did not got rewarded, then do the opposite. So let's see how these predictors look like in our dopamine, modulates dopamine activity. So the model-free action value update, as we would expect, it has a positive influence of the dopamine activity at choice time. So now the question, how does the model-based predictor look like? So we also see this positive modulation of dopamine at choice time, showing that model-free and model-based action value contributes to dopaminergic activity when the choice is made. Okay, so we look at how choice value affects dopamine activity. Then we wanted to ask how the second step value modulates dopamine activity. So first we look at what happened when the animal reaches the same second step as in the previous trial. So if we would expect that if in the previous trial got rewarded, to increase the value of that same second step, and if it didn't get rewarded, to decrease it. And we saw that what we would expect, that reaching the same second step as in the previous trial and it got rewarded, increased the dopamine activity when the second step information is available. However, one way also our mice could be learning this task is to actually learning the negative correlation between our reward probabilities. So if one second step port is highly rewarded and is good, the other second step port is have reward with lower probability, and then it's bad. So then we wanted to see what happens when the animal reaches a different second step state as to the previous trial. So we see that when the animal reached a different second step state as in the previous trial, and the previous trial was rewarded, dopamine activity decreases. So this is showing us that actually mice are learning a single latent variable about the state of the reward probabilities. Okay, so here we see like the summary of where we can see in ventral tegmental area. In here is also shown in pink that at lower time scales, signal is correlated with the reward rate. And now let's see in nucleus accumbens. So similarly as in VTA, we see a positive phasic update of reward. And also similar as in VTA, we see this, that signal at slower timescale are well correlated with reward rate. Then for the model-free and the model-based action value update, we also see this positive modulation at choice time. And then we found something very interesting for the second step value. And first we see this similar modulation when the second step state is revealed, but also very interestingly, in nucleus accumbens, we see that this modulation is reversed at outcome time. We still don't know like what is making this difference between VTA and accumbens, but we are trying to look into that. Then we also record from dorsomedial striatum because it has been also related with goal-directed actions. So let's see first what happened at the reward predictors. So here, very interestingly, we don't see this positive phasic update of reward in dorsal medial striatum, but we still see this tonic modulation correlated with reward rate. Then we also don't see any reliable update of model-free, model-based action value update, and neither of the value of the second step state. However, we found one behavior variable that massively explained dorsal medial striatum modulation, and this was the direction of the choice that was made. So whether the animal chose the side that it's in the IPSI or the contralateral side from where we were recording from, showing us that dorsal medial striatum encoded a contralateral initial choice independently of action or state values. So to conclude, we saw that choice behavior is consistent with model-based reinforcement learning, that there's a mixture of reward signals at different time scales, that VTA and accumbens encode value information respecting task structure, the anti-correlated nature of reward probabilities, and transition structure linking action and states. And this is consistent with recent work showing high-dimensional signals in the dopamine activity. And finally, that dopamine in dorsal medial striatum is primarily influenced by the direction of the animal's initial choice and action. So we hope that after this talk, we kind of show you that dopamine contains multiple representations beyond model-free reward prediction errors. So big thanks to Thomas Akam that we did this work together, and the supervision from Team Behrens and Mark Walton. Thank you.
All right, we've got time for a question or two. And Eric, if you want to go ahead and set up. Raise your hand. And if we're going to have a couple of announcements after questions, if you can hang around at least for those, and then we'll talk a bit about mind matching. Questions?
Yes.
Thank you. This is fascinating stuff. I was wondering if you could speculate a little bit about what exactly you think dopamine is signaling here. I mean, I see that it's encoding information about all of these putatively model-based variables. Do you think that that means that dopamine is participating in a model-based computation, or is it doing something else that might be linked to model-based computations?
Yeah, probably I think not. Like, we cannot say if actually dopamine is doing the computation, but probably is receiving this information maybe from other areas and then integrate it in dopamine, and this maybe would like update how you make you plan or you make your choices. But yeah, I don't probably dopamine is not doing the computation, but it's receiving some reference copies from somewhere else.
Maybe I can try to refine my question a little bit. So there are a bunch of different theoretical proposals existing already about the role that dopamine might play beyond traditional model-free reward prediction errors. So one idea could be that it's conveying some kind of generalized prediction error over non-reward features, and that could capture some aspects of what might look like model-based computations. Or another possibility is that there's some kind of model-based simulation that's, and then there's the model-free prediction errors are operating on those simulations from a model-based system. So I bring those up because I wonder to what extent your data can speak to any of those theoretical possibilities.
Yeah, I don't think that the way now we coded our regressors can like really answer this question, but we are now currently going to model our data and try to use the values and the data from those models into this and plugging it into our linear regression and see whether this our dopamine signal also is modulated by different variables. But I don't think our data now can speak into what kind of computations dopamine are doing.
All right, thanks.
Well, if there are no more questions, let's thank our speaker once more.